What's up, YouTube? Okay, so time for the final section of the tutorial. So that's running subtraction. This can take quite a long time, especially if you're running on several, like multiple epochs, a full data set. It has a couple of steps, a couple of extra steps that take a while, especially running cosmic ray projection on your template images and all of your science images. And then also the actual step where you do the difference imaging takes a long time as well. Okay, so let's get started. So this will be on a different object. So the object we'll be doing subtractions for is 18 cow. So I'm going to go to my data reduction directory and move into a new directory specifically for 18 cow. So let me copy a command from the tutorial. So these are 18 cow images, and you can see there are two epochs here. The first set of images are GRI images taken on 2018-07-01, and then we have a second set on 2019-08-31. Okay, so these later images are obviously going to be our templates, so after the object is faded below our limiting magnitude, so we're going to use these as the templates for subtractions. For this tutorial, I already provided you with pre-selected templates, one for each filter that we're going to do. In principle, we usually when we schedule references, we usually do multiple images per filter, and then you should go through, look at those images, and pick out which one looks like the best one to use as a template, as a reference for subtraction. So if one of them has a satellite going through it or something, then you should obviously not use that one. Okay, so the first thing we're going to do is that a lot of the steps of this reduction assume that things have already been run through our automatic pipeline, and especially it assumes that the template images, which are the first thing we're going to deal with, already have PSFs from our automatic pipeline, so we're just going to generate those really quickly, although we'll actually rewrite these PSFs in a second. Okay, this PSF's just got generated. The first thing we have to do is mark our template images as templates, and so there's this command to do that. First thing I'm going to do is just pull up the epoch of the templates. So there are these three images. One way to select single images is with this D flag. So D is short for ID, as in the ID number. So if I pick D87, then that'll pick out just the G-band image. So I'm going to pick that image and then do -s template to run the template stage. And so that will copy the file and mark it as a template image, so it knows and can look at this, so it knows what image to use as template for subtractions. Okay, so I'm going to go through and do that for each of the three images. So the ID numbers in this case were 87, 89, and 91. So I'll do that. This also pulls up the images in DS9 so you can look at them. Just double check that everything looks like it's normal. In this case, these images look good. There's this kind of weird spot at the bottom right, but I'll just ignore that. These are what our I-band images always look like. They always have this pattern on here. It's called fringing. It's just due to the width of the silicon chip being comparable to the wavelength of infrared photons, so they bounce around in it. So this is totally normal, nothing to worry about. Okay, so we've marked our three images as templates. So now if we want to actually look at those, we have to use this file type flag. So you can see we have our 3 images, GRI, and now they have temp for template in their name. Just to explain about file types, so file type 1 are normal images, so that's like the default version. 2 is unused. It was going to be used for merged and co-added images, but we never got around to adding that. File type 3 are for differenced images, so we'll use that later, and then file type 4 are for templates for references. Okay. So we have to run cosmic array rejections on our templates. So to do that, you just do -s cosmic, so we'll run the cosmic stage. All right, that's done. My computer's freaking out a little bit, but that's fine. If I pull up the list of images, then you'll see that they don't have any PSFs, so we have to make PSFs for them. When you make PSFs for template images, you should like make them very carefully, and I always run it with the show command so that I can watch in real time and make sure that everything looks good. That's because the PSFs we generate for our template images will affect all of our subtractions. So if you're subtracting 100 epochs, then the one PSF that you make for the template image will affect all of those subtractions. So you should like really double check that they're made well. So I have a couple flags that I'm going to use for these. So I'm picking more stars to average together. I'm excluding bright stars. And then you can also control the full with half max of the PSF from the command line. I'm running with a slightly smaller full with half max than usual. Usually I do like 5 or 7. I'm doing this because it was grabbing a star that had a source nearby, and so I'm trying to exclude that source from the PSF to make sure it's all nice and Gaussian. Okay, so this is the PSF. This looks pretty nice and symmetric and good. Looks like good quality data, so we'll say that's good. Okay, so here's the second PSF. Again, looks like it's selecting good, relatively bright stars, but not too bright. PSF looks nice and symmetric and good. Okay, and here's the last PSF for the I-band image. So again, looks like it selected pretty good stars. The PSF looks pretty symmetric. So that's good. Okay, so we've run cosmic array rejection and generated PSFs for the template images. You also have to run cosmic array rejection on the science images. So I'll copy over the command to do that and let that run. Okay, so cosmic array rejection is finished running on the science images. That always makes my computer freak out a little bit, but that's fine. So we have to make our PSFs for the science images before we run subtraction. So I'm going to run the PSF stage on them with pretty similar parameters to what I did for the template images. I'm again sort of cheating by letting the aperture correction be large. So in practice, you shouldn't really let that number be that big, but that's fine for now. All right, the PSFs for our science images have finished getting generated. So in principle, you should also go through and double check that these look good, so you can run the check PSF stage on these. I'm gonna skip that for now and go to the next step, which is the actual command for difference imaging. So let me copy that command. Okay, so this command has many arguments, so just to walk through them. First, we're picking our science epic, or science epics. This normalize keyword, you can either normalize them to the templates, which is T, or to the images, which is I believe. I usually normalize things to the templates so that everything's getting normalized to the same set of images, although that can give you problems if you're normalizing to Sloan templates, because sometimes those are weird, especially around galaxies. This dash capital T picks out the telescope for the science images. So you can see the telescope there is FL, which are our sinistras. Then you have to specify what the template date is. So for this set of images, the template date is 2019-0831. Yeah, you also have to specify what telescope your templates are on. This might be slightly confusing for non-LCO people, but FL and FA are for the same telescope, for the same 1 meters. Our cameras got slightly upgraded in 2018, I think. They got new controllers on them, new Archon controllers, which is what the A is for. So that's good. So we're specifying that our template images are 1 meters as well. Diff type, there are 2 different difference algorithms we use. Diff type 0 will run hot pants subtraction. Diff type 1 will run Paizogi subtraction. I typically use Paizogi for real reductions, for reductions that are going to get published. I think it does a little better job dealing with the background. Hot pants is significantly quicker though, so I'm going to use hot pants for now to show you. FixPix will run IRAF's FixPix algorithm, which can help with reductions. And then you also have to specify the stage, which for difference imaging is just called diff. So we'll let that run. That'll take quite a while, like 15 or 20 minutes probably, to go through all of them. All right, that finished running subtractions. Like I said, that process takes a while, takes like more than a minute per image. So it's typically the kind of thing that I set up to run overnight. I'll just start subtraction, in the afternoon sometime, and then just let it run, because it can take several hours, especially if you're doing a full data set for an image. So just to walk through what successful output looks like, it does print out quite a bit to the screen. I don't pay attention to most of it. The main thing I look for is, you can see right at the end, there's this big chunk of text that starts with insert, and then it's inserting a bunch of stuff into the database. So if it has this line, or it also says success, that's good. This means that it has successfully calculated the difference image and everything's going well. If it's missing this, then that means that it's failed and you should remake the PSF or look at the image or adjust something to get the difference image to be successful. Okay, so we're going to look at them. Like I said, file type 3 is used for specifying difference images. So if we do 2017, or if we do the same epic, but file type 3, then we can look at our differenced ones, which have diff in the name. Open up the DS9 window so that we can actually look at them. And just like for checking on PSFs and instrumental magnitudes, there's a check diff stage. So that opens up the differenced images, and then if you do frame tile, and then you can also go up here and do frame lock, frame image, cool. Then that lets you look at the science image, which is this top left one. The template image is in the top right, and then the actual subtracted image is in the bottom here. Okay, so if you zoom in, you can see there's clearly the galaxy and then 18 cow. And in the subtracted image, we've just got 18 cow left. So just looking right, zooming in on 18 cow, this all looks like a good subtraction. There's no evidence of the host, and things look pretty flat locally, so that's good. If we zoom out, the fainter stars got subtracted quite successfully as well, so that looks good. The brighter stars didn't do so hot, but that always happens whenever things are saturated or have spikes. That always messes with algorithms. So this looks like a successful subtraction. And then we can go through and look at the others as well. You can look at what the global thing looks like in the top right. So I usually check on the local environment and then also globally if anything looks weird in that top window. So all of these are looking pretty good. So that's a good sign. And in the I band as well. This one, the background looks a little weird to me. Looks like it has some extra texture to it, so that's a little weird, but we'll just continue with that for now. Okay, so for these difference images, you can see that they haven't been reduced at all, like they exist, but they don't have PSFs or instrumental magnitudes. So we've got to do all those steps. So these steps usually go pretty quickly for differenced images, so I'm just copying over running the PSF stage. So that stage runs very quickly because Hot Pants already has a PSF, so it knows what it is. So you just have to copy it to the right place, basically. So you can see that PSF column got filled in. So after the PSF stage is the PSF mag stage. I'm running it with these extra arguments, so -x1 and -y1. These set the order for fitting the background. So by default, the order is 3 to account for variations by being on top of the galaxy or by being near a galaxy or whatever. For subtraction images, the background should be flat, so I'm just specifying 1 for both of those. Okay, after the PSF mag stage is the CCAT stage for 0-point calibration. Normally you have to run this twice, once for Sloan images and once for Landau images, but we only have Sloan images, so we only have to run it once. And additionally, 18 cow is in the Sloan field, so we can specify that catalog. Okay, and then the very last thing to do is run the mag stage. For this specific reduction, you can see they have PSFs. The next column is the PSF mags, so they all have PSF mags. For some reason, they don't have successful aperture magnitudes. I'm not totally sure why that happened. But by default, the magnitude stage picks aperture mags for different images. Those don't exist for these, so we have to specify that we want to use PSF mags to calculate their apparent magnitude. So we can do that. So again, I'm selecting the images and running the mag stage, and then you can specify what type of magnitude you want to use. So fit is for PSF mags. I don't really know why it's named that, but that's fine. And then you can see they now have magnitudes and error bars successfully. Cool. So if you run the get mag stage, we can now look at our subtracted light curve. Okay, so these are our GRI images for this epoch. Intra-filter observations look consistent with each other, besides this last one looks kind of weird. When you run getMag on differenced images, instead of just showing just what the PSF extraction looks like, it also shows you what the subtraction looks like. So this was that image where I said the subtraction looked kind of weird, and you can especially see that weird background texture if you zoom in on what the PSF extraction looked like. But you can click through the other points and see what they look like as well. This takes a little bit longer to load because it's loading the full subtraction images. But yeah, overall the subtractions look pretty nice, and the PSF extraction also looks very clean. Looks like very flat noise after the PSF got extracted. So yeah, that's how to do subtraction. It is a bit of a longer process because that subtraction step takes a long time, and that can be iterating on that can be slightly annoying if you have to update PSFs or if something is not working. But other than that, it's basically the same steps. You have to make sure that you have to specify template images and then run cosmic ray rejections on your templates and your science images. You have to make sure everything has PSFs before you run the subtractions because the PSFs are used in our subtraction algorithms. Then you have to run the actual subtraction step and then do the 4 normal reduction steps, PSF stage, PSF mag, zcat, and mag stage on your subtraction images.